I'm Todd. Up to this point, you've solved right triangles using the Pythagorean theorem. And in this section, you're going to learn how to solve triangles other than right triangles using the law of cosines. So let's begin by reviewing the objectives. You'll learn the derivation of the law of cosines, solving triangles, and area formulas. Now, we can use the law of cosines to solve triangles when we're given all three sides of the triangle or two sides of the triangle with the included angle. So let's take a look at a couple of examples of these situations. We could be given side, 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 or three sides of a triangle. Here's an example. We have the triangle with the sides of length 7, 10, and 9. And it's important to realize that this triangle is unique, or there's no other triangle that I could draw that would have sides length 7, 10, or 9. Also, if I were given two sides and the angle included between the sides, and here's an example. I'm given the length of this side, which is 20, and the length of this side, which is 15, and the angle included, which is 46 degrees. There's no other triangle that I could draw other than this triangle, because when these lengths are specified and that angle specified, this length is also specified. So that there's only one length here that's possible. Now what we can do is we can use some of the rules that we learned from right triangles in order to derive formulas for triangles that are not right triangles. So here we have an example of a triangle. And this is triangle. We could label the vertices of the triangle A, B, C, and B. And if we put C at the origin, then the coordinates of that point would be 0, 0. The length of this side is B, which means the coordinates of A are B, 0. And then we could establish a point up here, capital B, with coordinates x, y. And of course, x and y could be any positive numbers here in this case. So if we drop down a perpendicular here, we can recognize that the length of this perpendicular is y, and the length of this side from here to here is x. And in fact, this forms a right triangle. So what we have is the legs of a right triangle, x and y, and we have the hypotenuse A. Now, what we're going to try to do is to create a formula for A using the angle gamma. What we can do is create relationships between A and x using the cosine and sine functions. For example, we have cosine gamma, which is equal to the side adjacent, in this case that's x, divided by the hypotenuse, which is A. So we get cosine gamma equal x over A. The sine of gamma is equal to the side opposite, which is y, divided by the hypotenuse A. Now if we solve each of these equations for x and y respectively, we get x equal A cosine gamma and y equal A sine gamma. What we're going to do now is we're going to create a formula for C using the distance formula. And here's what we can do. We're interested in the length of C here. And so we're given 2 points. We're given the endpoints of C. We know this endpoint is B0, and this endpoint is xy. So using the distance formula, we know C is equal to the square root of the quantity x minus b squared. These are the x coordinates of the endpoint, plus y minus 0 squared. These are the y coordinates of the endpoints of that line segment. Now, we just found the x is equal to A cosine gamma, and we just found that y is equal to A sine gamma. And in this step, we've also squared both sides. So we have C squared equals A cosine gamma minus b squared plus A sine gamma squared. Now, if we square these two out, we get A squared cosine gamma, or cosine squared gamma, minus 2AB cosine gamma, plus b squared, plus A squared sine squared gamma. Now, if we group these terms together, this one, and factor out the A squared, we get A squared times cosine squared gamma plus sine squared gamma. This is equal to 1. So we get A squared there, plus this b squared minus 2ab cosine gamma. So what we found is a relationship between c squared and ab and the gamma. Now, here are the three forms of the law of cosines. Instead of gamma here, we're going to use alpha, beta. Oh, actually, I'm sorry, gamma's down here. So this is the one that we actually derived. So any triangle with standard labeling satisfies a squared equal b squared plus c squared minus 2bc cosine alpha. B squared equals a squared plus c squared minus 2ac cosine beta. C squared equals a squared plus b squared minus 2ab cosine gamma. Okay, now let's use the law of cosines in the following example. We're asked to solve the triangle and approximate the values to the nearest tenth. Now, what we're going to do is, what we're actually looking for is the length of this side over here and this angle right here. So let's see, the angle opposite alpha, that would be, the angle opposite A would be alpha, and the angle opposite, this should be gamma, that's the angle C, and then this would be the angle beta. So what we're going to do is we're going to find the length of this side first. And so we could think of that side as little a, or lowercase a. And so the formula we're going to use is a squared equals b squared plus c squared minus 2bc cosine alpha. All right, so b squared is 4 squared. B is 4, so I'll replace b with 4. C was given b 5, so we have 5 squared. So we have minus 2 times 4 times 5. And alpha was given, it's 43 degrees, so we have cosine of 43 degrees. So if I take the square root of both sides, a equals the square root of 4 squared plus 5 squared minus 2 times 4 times 5 times the cosine of 43 degrees. Now, if we simplify this using a calculator, we find a is approximately 3.4. So what we found was the length of this side is 3.4. Now, the next thing we'll find is the angle beta. So we're going to use, now that we have the lengths of all three sides, we can use the angle beta, or find the angle beta as follows. B squared equals a squared plus c squared plus 2, actually this is minus 2 ac cosine beta. Now, if I solve this equation for beta, I get the following formula. Beta equals the inverse cosine of the quantity a squared minus b squared plus c squared, all divided by 2ac. Now I'm going to substitute in the values for a, b, and c. So we get the inverse cosine of 3.4 squared minus 4 squared plus 5 squared, and all that's divided by 2 times 3.4 times 5. All right, now, evaluating this on our calculators, we get beta is approximately 52.8 degrees. Now we can find gamma. Since we have alpha and beta now, we can find gamma because we know the sum of all the angles has to be 180 degrees. So gamma must be 180 degrees minus 43 degrees minus 52.8 degrees, and that's equal to 84.2 degrees. So we found the two missing angles and the length of the missing side. Now I'd like you to try this next example. In this example, you're given that a triangular truss is shown in the figure, and you're asked to find the angle theta. Now you have the three sides, and you have the angle theta. Now, you can think of this angle as alpha if you like. We don't have a formula for theta, but you can use the formula for alpha and just substitute theta. So go ahead and stop the tape and try this. Okay, now I'll try the problem. What I'll do is label the vertices for convenience. Call that one A, this one B, and this one C. Now the formula we'll use is a squared equals b squared plus c squared minus 2bc cosine alpha. And like I said, the angle we're looking for is actually theta, so we can just replace alpha with theta. And we have a squared equals b squared plus c squared minus 2bc cosine theta. Now, if we solve this equation for theta, we get theta is equal to the inverse cosine of b squared plus c squared minus a squared, all divided by 2bc. Now, if we substitute the values we were given for b, c, and a, we end up with the inverse cosine of 20 squared plus 16 squared minus 13 squared, all divided by 2 times 20 times 16. And evaluating this on our calculator, we find theta is approximately equal to 40.5 degrees. Now, we can also use the law of cosines to develop some formulas for the area of a triangle. In any triangle with standard labeling, the area K is given by K equals 1/2 AB sine gamma, K equals 1/2 AC sine beta, K equals 1/2 BC sine alpha. So let's use these formulas in the following example. We're asked to find the area of triangle ABC in the figure. So we're given the length of side A, the length of side C, and the angle in between, 55 degrees. So what we'll do is we'll use the following formula for the area. The area K is equal to 1/2 AC sine beta. We were given that A is 34 and C is 42 and beta is 55 degrees. Now, evaluating this on our calculator, we get approximately 584.9 square feet. Okay, now, there's another formula called Heron's formula that allows us to find the area of a triangle when we're given all three sides of the triangle. If a triangle has sides with lengths A, B, and C, then its area K is given by K equals the square root of S times the quantity S minus A times the quantity S minus B times the quantity S minus C, where S is equal to 1/2 the quantity A plus B plus C. Now, Heron's formula is very useful in surveying applications when we're trying to find the areas of plots of land that have irregular shapes. And here's an example. We're asked to find the area of the parcel of land determined by A, B, C, D. So we have this trapezoidal shape, and we want to find the area of it. Notice if I divide this trapezoid into two pieces, I end up with two triangles. And we're actually also given that the length from C to B is 125 feet. Now, the way I'm going to do this problem is I'm going to call this area K1 and call this area K2. So I'll use Heron's formula to find the area of K1 and K2 and then add those two areas together. So we'll start off with the area of K1. The first thing we have to do is to find S. And so for the first triangular region, S is equal to 1/2 times the quantity 125 plus 85 plus 100. Simplifying this, we get 155. So using Heron's formula, the first area, K1, is equal to the square root of 155 times 155 minus 125 times 155 minus 85 times 155 minus 100. And if we multiply if we simplify the radicand here, we get the square root of 17902,500. I guess that's 17,902,500. And then evaluating this on a calculator, we get 4,231.1 square feet. So that's the area of the first triangle. Now let's find the area of the second triangle. Again, using Heron's formula. We'll start by finding S. S for this triangle is 1/2 125 plus 105 plus 60. And evaluating this, we get 145. So K2 is equal to the square root of 145 times 145 minus 125 times 145 minus 105 times 145 minus 60. This gives us the square root of 986,000, 9,860,000. And approximating this on our calculator, we get about 3,140.1 square feet. Now all that's left to do is to add those two areas together to give us the area of the region we're looking for. So the area K is equal to K1 plus K2. We just found K1 is 4,231.1 square feet, and we're going to add to that 3,140.1, and this gives us 7,371.2 square feet. So the area of the plot we were looking for is 7,371.2 square feet. Well, in this section, you've learned about a very useful formula called the Law of Cosines, and you've learned about a couple of area formulas as well. So be sure to do some examples out of your textbook, and I'll see you next time.